Hi, and welcome back to day 2 at Rapid Plus TCT. I'm Brandon Ribic, the Technology Director at America Makes, and I'm happy to be joined this afternoon with Davide Marini from Inkbit. How are you doing today, sir? It's great to see you.
Very well, and thank you for pronouncing my name perfectly.
Thank you so much.
Looks like you speak Italian.
I try.
I'm originally from Italy.
Okay.
I come from a town called Brescia. It's on the northeast, 1 hour east of Milan.
Okay.
I went to engineering school in Milan, mechanical engineering, and then I started working in London, and then I came to the US for my PhD. I did my PhD at MIT.
Oh, nice.
Also in mechanical engineering, but with a focus on biomaterials.
Oh, cool.
And then I eventually became passionate about entrepreneurship. So I launched my first startup, which was called Firefly Bioworks.
Okay.
In the field of life sciences. And then eventually, when that company was acquired, I looked for new opportunities and I became fascinated by 3D printing. I didn't know the field at all. Okay. But I was introduced to Professor Wojtek Matusik at MIT, who is one of the co-founders. Mm-hmm. He's a professor of computer science and artificial intelligence at MIT. And so he had invented this new method of 3D printing that essentially takes traditional inkjet printing to the next level by integrating machine vision into it. So typically inkjet works by, you have a printhead that jets droplets of typically a photopolymer. And then in order to ensure that the part comes out accurately, every layer is scraped, so to speak, is flattened with a mechanical mechanism, with a roller typically, so that you know that you're always starting from scratch, from flat. So that is the traditional design that was pioneered by Stratasys. So in our case, the advancement of our technology is that we no longer need mechanical flattening. Okay. Instead, we use a vision system that we designed that scans each and every layer after deposition, creates a topographical map, three-dimensional topographical map at voxel resolution, and based on that map, it will remap the following layer. So it's really an in-process inspection, control, and reaction. So it's a true vision-based feedback control closed loop.
And so you mentioned your colleague has expertise in artificial intelligence, machine learning. Does it use those advanced analytical techniques in terms of that adaptive capability?
We do. We do two types of corrections. One is corrections of random imperfections. As you know, in inkjet, the droplets are not always the same size. There are always some minor imperfections. So you always have to adopt some type of correction mechanism. Okay. So traditionally, you use a scraper. We don't. We basically create a topographic map. And if there are any, say there is a valley, in the next layer, the machine knows and will deposit into that valley. Wow. Of course, because we have access to so much data, we can take advantage of this. And we can also introduce machine learning mechanisms to enable the printer to learn the particular behavior of each material to increase reliability and precision. But what's interesting is that we started life by wanting to make a more accurate, more reliable, more repeatable inkjet process by introducing this vision system. But what we found was that, interestingly and counterintuitively, the biggest advantage of our process, in addition to the precision, is actually the type of materials that we can use. Okay. So we are no longer bound to acrylate chemistry. Like every photopolymer-based 3D printing process out there today has to use acrylate chemistry. And the reason is because you have to control the polymerization both in space and time. Okay. So in an acrylate-based process, what you can do is that you shine your UV light, then when you stop, the reaction stops. Okay. So, but that limits the type of polymers that you can create. So typically, if you look, for example, at what traditionally inkjet is known for, is for beautiful prototyping parts that are very faithful to real life, but the materials are known to degrade over time, so they cannot be used in production.
Okay.
So we no longer have this limitation. There's no acrylic chemistry in our materials.
Wow.
Because of the vision system.
Sure.
So and this is slightly counterintuitive.
Yeah.
Yeah, so the reason is this. Typically most of the most interesting photopolymers are called dark cure chemistries, which means that once you initiate the reaction, typically by UV, you cannot stop it.
Okay.
So for example, now one of the most interesting materials that we have is a highly chemically resistant epoxy resin that is a dark cure resin. If you tried to use that resin on a traditional inkjet design, the moment you pass the roller on top, the resin will stick to the roller and will cure on top of it because it's a dark cure, it continuously cures.
Okay.
So, and it will jam the machine. It's just not usable.
Sure.
So, having introduced a vision system, having made the process contactless, opens up the world of dark cure, continuously curing chemistries to us. And it's basically one of those serendipitous finds that we did not really expect. That turns out to be one of the most important advantages of our process.
Yeah, that's really interesting.
Yes.
I imagine along with all the data you're capturing about the process, does that offer your customers an opportunity to better understand the as-built quality of the material as well?
Yes, that's a great question, yes. I forgot to mention that because we scan each and every layer, automatically the machine creates a stack of layers during the print. So all we have to do is just stitch those layers together and you essentially obtain the equivalent of a medical CT scan of every part.
Okay.
So every part comes with a digital replica of the entire process.
Wow.
And this is particularly important for maybe intricate geometries. We are very good at making small, high aspect ratio channels down to about 0.5 millimeter. You can make very long channels, very intricate geometries. And how do you know that the geometry internally is correct? So we know because we have access to all those data.
You're measuring.
Yes.
That's interesting.
It's one of the advantages of having a vision system.
Sure. And so you mentioned the channels, you mentioned the breadth of materials that you can effectively utilize. Where are you applying this technology today? What markets, what industries?
Yeah, so we now are exploring a lot of different applications, but the areas where we have found the most traction, the most interest is the medical field.
Okay.
As you can imagine, if you can make soft, very compliant parts and at the same time having a very faithful process and very intricate geometries, there are all sorts of applications. I cannot disclose the partnerships that we have, but just with your imagination, imagine conformal devices that conform to the body, wearable devices, but also I'm very intrigued by the field of drug delivery.
Okay.
And all sorts of applications that require multi-material capabilities with intricate geometries that lend itself to reservoirs, and things of this nature.
Exciting.
Yeah.
Also,
really we see a lot of traction in the robotics field, especially in soft robotics, because now the field is booming. All these grippers and actuators that are pneumatically actuated, they tend to rely on a combination of rigid and soft structures.
Yeah.
So traditionally they were molded with silicone. But with our process, it's natively multi-material. So we can have, for example, a robotic gripper that combines rigid structure like bones in a human hand together with very soft skin on the outside.
Wow.
Yeah. Another traditional application that we are exploring with a Boston hospital is medical models. Okay. In particular, there are some procedures that require students to be trained on making incision.
Yes.
That results in a lot of blood loss.
Sure.
So in order to be able to train students on those procedures, we're developing essentially a skin that contains lots of veins and small channels that we can fill with fake blood to mimic the behavior of real skin.
You know, I'm curious because you mentioned the medical applications, you mentioned the analytical technology that you're leveraging. And seeing how things in the medical field are evolving, especially with robotic-assisted procedures now, Are there opportunities there that maybe you're trying to explore the utility of your algorithms and software and machine vision to help augment procedures in
Wow,
in
it's
the
interesting.
OR?
I have not thought about this,
Okay.
but it's a very interesting thought. It's a very interesting thought.
I'm learning myself. I was so surprised in
If
the
you
last
have-
year to see this.
Yeah,
So
no.
yeah, it's remarkable.
Yeah, no, thank you. We are always looking for partners that are willing to test our technology. So if you have friends in that specific field, I would love an introduction.
I'm happy to make an introduction.
Thank
We're all
you,
about
thank you.
collaboration at
Thank you so
America
much.
Makes. So
Thank
yeah,
you.
no, it's wonderful. And thank you, sir, for your time. I really appreciate you
Oh,
joining
you're
us
welcome.
here
Thank you for
today.
inviting me.
Yeah, it's been a great conversation.
Thank you so much. Thank
You're
you.
most welcome.
Thank you.
Enjoy the rest of your time at Rapid.
Oh, same to you. Thank you
you.
so much. Thank you.